Hello, 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 everybody, and welcome to Recitation. Uh, Now, you may be wondering, hey, wait, we just had like Halloween recently, so is he gonna do like anything spooky? Well, I have some spooky for you. I got spooky, 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 spooky. It's the spooky recitation. That's the only thing that's going on around this time of year. We can pretend like that's going on for this recitation. So this is going to be the spookiest I can get, because I didn't really have time to prepare anything spookier. So this is what you guys have to deal with. Like to talk about music at the start. You Say Run, amazing song. Truly goes with anything. The Giles theme of anime themes, probably. That wasn't actually a request from anyone. I just wanted to play that at the start of recitation. Gotta have to pick out what I want to do for next week, because I already know what I'm going to do for the last recitation. So I'll have to pick out a good one for next week, too. Regardless, let's go ahead and hop right into it. Our weekly recitation stuff. You've got a homework that is due this Friday. That's your pattern matching homework. Definitely recommend starting that now. That way, that if you have issues, you can come into office hours and ask about it. We're going to cover everything that's going to be on this today. So definitely you'll have a good chance to get started. Because especially Friday, our office hours tend to be a little bit sparser just because it's Friday and not everyone is free. And I need to cancel my office hours on Friday, unfortunately, so that's going to kind of leave a pretty big gap. So definitely get started today. That way, if you need help, you can come into office hours like Wednesday or Thursday, which might be a little bit better for you. Your last homework, homework 10, is going to release the same day. That's a 2-week homework due on the 20th. That's on graphs, which we'll get to next week. That is the final homework in this course. There is no homework 11 or anything. Don't worry about that. Is the homework not due Monday? This is not what anything I have says. Can one of the other TAs that's watching this message Robert and figure out what's going on with that? And then get back to me. But regardless, I think these dates are accurate for homework 10. Exam 3 is... Oh, one thing I want to mention just early on. You'll notice in the announcement... Yeah, you'll notice in the announcement I sent out this morning with the recitation links, I also posted the examples I'm going to do later. So if you want to like take some time early on and write all those examples down, just because like those big tables take up a lot of space and can be timely to write down, I've got them early so you can write those down in advance. But I'll still give you a little bit of time once we get to them. Exam 3 is the big thing. That's next week. On the 11th, so a week from tomorrow. That's your final exam, well, not your final exam, your last regular exam before the final exam. It's going to cover basically stuff through pattern matching. I'll send a topic list out for that tomorrow, so be on the lookout for that. The practice exam solutions, I think you can already see them if you do like the Canvas version of the practice exam, but I'll still release like the PDF solutions on the Sunday before at noon. They're already scheduled to be released, so I can't screw them up. You've got your worksheet on Canvas, and there's only 2 recitations left after today. There's not going to be a recitation on that 24th. It's that day before the Thanksgiving break. I'm actually going to be home already by then, so there's not going to be any recitation or anything. We normally don't have recitation then, so that's not a big deal. The stuff we're going to do today is just the remainder of the pattern matching algorithms, so Boyer-Moore, Kmp, and Rabin-Karp. I'm going to assume that you remember like the basis of pattern matching that we talked about last week, so what we mean when we say we're doing a pattern matching algorithm, and what brute force was, and why it sucks. With that said, let's go ahead and hop right into it with Boyer-Moore. So Boyer-Moore is our first big pattern matching algorithm other than brute force. It's, as all of the algorithms we're going to talk about today, it is some improvement on brute force. How Boyer-Moore is going to do it is it's going to skip matches where we know that a match is impossible, just based on where characters are. And how it's going to do that is it's going to get its information from mismatches. Now, this is something I personally like to stress a lot, and you'll see it in relation to KMP. But how Boyer-Moore gets the information to do these crazy shifts you're going to see is always from mismatches. So if we get mismatches in Boyer-Moore, we can do cool things. If we get matches, we might not be able to do anything interesting. how we're going to get and use this information is we're going to construct what we call a last occurrence table. And that last occurrence table is going to be for all of the unique characters in our pattern. So this is going to be some pre-processing on our pattern. Before we even start looking at the text, we're going to look at our pattern first and construct this last occurrence table. And this table is going to let us do a more optimal realignment after we get these mismatches. Remember, the mismatches are where we get information. So how a last occurrence table works is it's going to map each character in the pattern to the last index the character occurs at. We're also going to add as an extra stipulation that for any character that is not in the pattern, we're going to say that it maps to -1. Something that you can use that's interesting in like the hash map class is there's this get or default method, which basically says if my key is in the hash map, get its value. If my key is not in the hash map, give me back some default value that I'm specifying. Because this is, I call it a last occurrence table, but this is a hash map. Which is weird because we're going to have another table we talk about today, which is an array. So I want to specify this one's a hash map. So let's do a quick example. We've got our pattern here, this word Shanghai, and this is the last occurrence table we're going to construct. So all we need to do is just iterate through the pattern, and every time we see a character, we just update it in our table. So we see S at index 0, so we can put that in the table. We see H at index 1, so we can put that in the table. A at index 2, N at index 3, G at index 4. We see H at index 5. Remember what happens when we try to put a duplicate key in our hash map? We overwrite that old value. So now we have a 5 in there for H. Same thing with A. We're going to overwrite this too, and now we have a 6 in there. Then 7 is I. And usually in diagrams, we represent this with this asterisk -1 to indicate that everything else has a value of -1. Now, don't actually loop over every single character and put it in the hash map with value -1. That is inefficient. You can just use this getter default method, or you can basically write it yourself as if it's contained, return its value, otherwise -1. It's pretty straightforward, but don't actually try to put everything else in the hash map. All you need to put in the hash map are the characters that you have in your pattern, and you can just loop over all of them and call put repeatedly. The actual construction of the failure table is really easy. Just be aware that there are some times where you might not need to construct the failure table, or the last occurrence table. For example, if you know that before even doing any comparisons, if you know that it's impossible for your pattern to exist in your text, try to think about what might cause that. If that's impossible, then there's no reason to construct a last occurrence table, because there can't be matches anyway. So that's your challenge problem for the day. Try to think about when that's possible. I'll give you a couple more seconds to write this down, then we'll go more in depth on what the Boyer-Moore algorithm actually looks like. Alright, sorry about that. Okay, I've gotten confirmation that, yes, homework... One second. The homework 9 was supposed to be due on Monday. It was an error in my notes. So, yes, homework, as Gradescope says, it was actually supposed to be due on Monday. So, sorry about that. That was me. Thank you for my TAs getting back to me with that. Alright, now let's talk about the Boyer-Moore algorithm. So a lot of this pseudocode is available in the Sai Krishna slides, but I'm still going to walk through it. This goes a little bit off the page. That's as much as I can get. There's your screenshot with all the pumpkins. So remember that in these pattern matching algorithms, we usually say that I is our alignment of the pattern to the text, and j is the current character in the pattern. What this means is when we do these comparisons, we're comparing text at index I plus j and pattern at index j. So there's actually a couple different ways to like use these pointers. So you might not use I and j, especially for like Kmp. Some people use a k pointer. It's the same algorithm, just different names for the pointers, and they represent slightly different things. So you can use whichever implementation you want as long as it follows this basic algorithm. So Boyer-Moore is a little bit strange in that it's going to start comparing from the back of the pattern. Now, the back of the pattern is not the back of the text, so we still start at I equals 0. That's the front of our text. But we start at j equals to m minus 1. Remember, m is the pattern length. So this means that our first comparison is comparing text at m minus 1 to pattern at m minus 1. So that makes sense. You'll see it on the next page when we start doing our algorithm. Now we have these different cases. If we have a character match, we decrement j. That indicates going on to the next character in our pattern, which is actually kind of the previous character. But you get the point. When we're starting from the end, decrementing j is starting here and moving this way. If we get a full match, which means that we decrement all the way down, match at j equals 0, and then decrement it to -1. That's what I mean when I say that a full match is j equals -1. What we're going to do is we increment I. I got messed up, but that is an I. So incrementing I means shifting over by 1, and j just gets reset back to m minus 1, that end of the pattern. Now, this will seem a little bit strange. Well, I'll get to that later. That'll make more sense if I talk about it later. Sorry. If we get a mismatch, remember, this is where the real meat of Boyer-Moore is. What happens when we get these mismatches? What we're going to do is we look at the character in the text that caused the mismatch. So we see what character in the text didn't match to our pattern. If that character is not in our pattern at all, which remember, we can check that in O of 1 time using our last occurrence table, we can shift our pattern completely past it, because no alignment of the pattern with that character can possibly be a match if it's not in the pattern. So if your pattern has like all A, B's, and C's, and you encounter an F in the text, you can't possibly match up the pattern as long as that F lines up somewhere in the pattern. You'll see examples of that on the next page. Otherwise, if the character is in our pattern, what we're going to try to do is we're going to try to realign the last occurrence with the character with that occurrence of the character in the text. But we have to make sure we never move the pattern backwards. If doing this realignment would have caused our pattern to go backwards, we're just going to shift it forward by 1 instead. How that works in terms of like code and math is we get that value from the last occurrence table. So last occurrence table of the failed character, this is from the text. So what character in the text we failed with, I'm going to call that shift, whatever number that is. So that could be a -1, or it could be something between 0 and m minus 1, any of those things. If that shift number is less than j, then what we're going to do is we're going to have increment I by j minus shift. So this is I plus equals j minus shift. Otherwise, this is going to indicate what would happen if we tried to move backwards. We're just going to increment I by 1 because there's nothing else we can do. In either case, we're just going to restart comparing from the back of our pattern. So j is going to get reset to m minus 1. And then we continue going forward and doing this loop. So we'll give people a little bit longer to write this down, ask questions about it, or take a picture. And then on the next page, we're going to do an example. So if you want to start preparing for that, you can see what the example text and pattern are on Canvas in that announcement. Right, hopefully that's good. People can always pause on this if they need a little bit more time. But otherwise, let's go ahead and move on to our first example. If I'm not wrong, I think this is the first time I've written down any of these note pages in landscape and not in portrait. Everything looks like it should fit nice with even within the pumpkin and spooky frame. So let's see. This is our text here at the top, this really long string. You can see it on canvas if you want it not in my handwriting. And this is our pattern, abacaba. And we're going to use the Boyer-Moore algorithm to try to find all of the occurrences of abacaba in this text. So I've written down here our last occurrence table. I just kind of did it for you guys because this last occurrence table is pretty easy to see. You can see that A is at index 6 is the last occurrence of B is at index 5, C's only occurrence is at index 3, and then this star -1 is kind of a constant thing for Boyer-Moore. So we'll start doing our comparisons. Remember, we start from the back of the pattern, even though it's still aligned with the front of our text. I'm going to do a circle every time a comparison happens, and I'll draw a line through it if that comparison is a failure. So this one's a success, which means we go backwards. Now, I have a comparison here, but it failed. So what happens is I look in the text, I see I mismatched with a C. Then I look in my failure table and it says, oh, you've got a C at index 3. So what I'm going to try to do is I'm going to try to line this C up to match up with that C in the text. So without doing any math, just from a diagramming perspective, I can very easily write out what it should be. So this is what we expect. We want these two C's to line up. Now, if we try this in math, what happened is we got that shift was 3. At that moment, J was equal to 0, 1, 2, 3, 4, 5. I was 0. So what we did is I equals I plus J minus shift, which is the same thing as saying 0 plus 5 minus 3, which is 2. You'll notice I is at index 2 now, because index 2 is the beginning of our pattern. And then we reset J back to the end of the pattern. That's just going to mean we start comparing from this A again. We don't start at that C, because while we know that the C will match up, we don't know anything else. All right, let's start again. We do a comparison here. That's a success. These A's match up. Then we do a comparison here, and this one fails. You'll notice that the character in the text we failed with is a D. Now, there's not a D anywhere in our pattern. We can see that in our last occurrence table really easily. So what should happen is I should move my pattern completely past that, because any alignment that matches up with this D, there's no chance of that succeeding. So what I expect is this. Completely past that D. And again, we can see this if we do the math. We'd get that shift was -1, J is 5, I is 2. So I is going to be 2 plus 5 minus -1, which is going to be 8 overall. And we can count 0, 1, 2, 3, 4, 5, 6, 7, 8. And index 8 is where our text and pattern are currently aligned. So that math works out. I'm not probably going to do it for the other examples because you can see how it works, and from a diagramming perspective, it's pretty clear. So we start comparing again. This A mismatches with this B. Now, we've got our B in the last occurrence table. We can try to line them up. Remember, we're only trying to line up the last occurrence. We start comparing from the end again. A, B, A. Now this C is going to mismatch with the B. So what happens is we look at our last occurrence table and it says, oh, there's a B at index 5. You should try to line that up. But if we try to line up the B at index 5 with this B right here, we would have to take our pattern and shift it backwards. In fact, you can see that we'd have shift equals 5, but J equals 4. And you see that here, J is less, here J is less than shift, so this would be a shift backwards. So we're never going to do this. In any case, whenever this would happen, we're just going to shift forward by 1 to avoid that issue. So you see we just shifted our pattern forward by 1 because we weren't able to do any more intelligent shift than that. Start comparing again. We mismatch with this C, so we're going to line the C up. Now we start comparing again. A, B, A. C, A, B, A. Everything matched. So this means we found a match at index I, whatever I happens to be in this case. You can count it for yourself. So what do we do after a match if we're trying to find all of the occurrences? Well, remember I said Boyer-Moore gets its information off of mismatches. So if we get a complete match, we didn't get any information because we never had a single mismatch. So all we can do is just shift forward by 1. Then we start doing this comparison. It's going to fail. And what would happen is we can try to do this shift over to line up this B with this B, but that's going to shift our pattern past the edge of our text. We're going to have characters that kind of hang off the cliff here, and that's going to be our indication to stop. So usually we won't even write out that last shift. We don't even count it as a shift. We just stop right here, and we say that this is it. So if we count these circles, we can see how many comparisons we did. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 comparisons total, which is pretty good because this is a long text. I mean, this text has more than 18 characters, I think. So we didn't even look at every single character. Someone asked, is there a reason why we align the last occurrence and not the first? You could do it with first occurrences comparing from the beginning too, but I think last occurrences overall work better, and they fit more situations a little bit better, and they also, something we have on Canvas under our, like, the content papers and other resources. There's a paper made by the former dean of the College of Computing, Zvi Galil. He's actually a current professor that teaches automata and complexity. He has some optimizations that work well for this algorithm that can improve upon it a little bit more. Obviously, nothing you have to do for your homework, but it lets us take some of these worst-case situations that we'll talk about and make them a little better. But I don't know if there's a particular reason why this algorithm is done with the last occurrences. I think it just works better and fits better overall with getting these better efficiencies. Because if you did first occurrence, you would have to like start at the end of the text to get all these nice cases. And starting at the end of the text isn't always something that's possible in practice, because you might not always have access to the full text. Otherwise, a couple more seconds, write this down, then we'll get on to the efficiencies, and then on to our next algorithm. All right, let's go ahead and move on. Now, you'll remember last week when I talked about efficiencies, I said that average case of a pattern matching algorithm isn't really the most meaningful thing in the world. Boyer-Moore is the perfect example of that. We don't really have a well-defined average case, and you'll see that's because the best and worst case are just so far apart. So we're not going to care about the average case for Boyer-Moore. Worst case is a little bit clearer. If we mismatch on the first character of the pattern every single time, now when I say first character, I mean like j equals 0, not like the end of the pattern, which is the first character we compare. So if we had like a pattern that's BAAAA and a text that's all A's, you'd see we compare on this character, compare on this, fail on this, shift forward by 1, compare, fail, shift by 1, over and over and over again. And it just becomes a brute force comparison starting at the other end of the pattern. That's where we get this O of m times n. So not anything good, not anything we really want, but you can imagine that something like this is very rare compared to with brute force. You're going to do a lot of comparisons even in common cases. Best case, if we are only looking for the first occurrence, as I mentioned last week, trivially, that's O of m. If you find the first occurrence immediately, you don't have to do any other work. But the all occurrences is what we're really going to look at. And that is going to end up being n divided by m plus m. Now where this plus m comes from should be really obvious, because at the very start of the algorithm, we have to loop through our pattern once and determine our last occurrence table. So that's going to give us a plus m. Where this n over n comes from is this comes from always doing those big shifts. So if we always shift by the full length of our pattern, we can make huge gaps, huge strides with this search. So if our pattern is all A's and our text is all B's, we would compare this first A, fail, shift by 5, compare the A, fail, shift by 5, over and over and over again. And that's a total of n divided by m shifts to get to the end of our text, where we're obviously done at that point. So this is really nice. This is the first time we've seen division in a big O, and you can imagine that as these numbers start to get big, that's going to be very significant in cutting down the time complexity of how this algorithm runs in practice. So Boyer-Moore, super nice algorithm. I think like the grep tool, if you're familiar with that, it's a string searching tool, that does use Boyer-Moore because it's very useful in general situations. In particular, Boyer-Moore works well when there isn't a lot of overlap between the characters in our pattern and the characters in our text, because that's going to give us these full-length shifts a lot more often. This generally happens when we have like a large alphabet. So if you think like if we're looking for case-sensitive things in the English alphabet, that's 52 characters to look at, because the 26 lowercase and the 26 uppercase. So it's very likely that we encounter characters in our text that aren't in our pattern, and we can do these huge shifts. So with large alphabets, Boyer-Moore is going to work very well. A couple more seconds on that, then we'll move on to Kmp. All right, let's go ahead and move on. Kmp, Knuth, Morris, Pratt. How this is going to work is, in a lot of ways, Kmp is kind of analogous to Boyer-Moore. So it's really nice to teach both of them. You'll see when we get to our third algorithm, Rabin-Karp, that it's kind of different. But Kmp and Boyer-Moore have a lot of parallels. How Kmp works is it's going to utilize matching prefixes and suffixes in the pattern to avoid comparing characters that we know are correct. You remember Boyer-Moore tried to avoid alignments that we knew were incorrect. Kmp is going to just try to avoid doing extra work if we know characters already match up. How that works is Kmp is going to get information from matches. So Boyer-Moore got information whenever we had a mismatch. Kmp is going to gain information slowly every time we match characters, and then when we get mismatches, we can use that information we've gained to do intelligent shifts. So you might imagine, because Boyer-Moore, which gets its information from mismatches, only got to shift by 1 whenever we had a complete match, you can imagine that Kmp is going to have to not do very intelligent shifts when we have no matches at all and we mismatch on the very first character we compare, because that's gotten no information so far. So that's a little bit of food for thought looking forward. Now, how we do it this time is we're going to pre-process the pattern to construct a failure table. Now, I promise you, and I can say this for certain because I think I've already messed it up, at some point, me, another TA, or the professor is going to say failure table instead of last occurrence table, or last occurrence table instead of failure table. They're both called table, and we talk about them near the same time, and it's really easy to say the wrong one by accident. Last occurrence table for Boyer-Moore, failure table for Kmp. I apologize in advance if I ever screw that up again. Now, what is this failure table? Because it's a lot less clear than last occurrence table. We're going to say that our failure table is defined so that index n of the failure table contains the length of the longest prefix-suffix match if we only look at the pattern in the characters up to that point. So that's like characters 0 all the way through n-1, if you think about it that way. Or index n, up to you, however you define it. But we're looking for these prefix-suffix matches, and you'll see that when we do our table. Now we've got this cool algorithm here. Now, something, obviously, I have this written here just because it's convenient, but I have this, like, PI and I have this PJ here. Those are looking at the character in my pattern at index I and the character in my pattern at index J. Obviously, this does not work in code. You can't, there's no way to actually like index your pattern like this. Don't do it. But for the sake of diagramming questions, or for the sake of like writing out pseudocode, I'm obviously doing it because it makes sense. Also, I want to specify this is an int array. The last occurrence table for Boyer-Moore was a hash map. This is an int array. So these f of j's, those actually make sense. So we start I at 0, j at 1. And what we're going to do is while j is less than our pattern length, so while j hasn't gone past the pattern, if our I and j match up, what we're going to do is we're going to fill in that spot of our failure table with I plus 1, increment I, increment j. Otherwise, if they're a mismatch, if I is equal to 0, we're just going to set that spot of our failure table to 0 and then increment j. Otherwise, we have this weird I equals f of I minus 1. And we'll get to examples of what all these mean and why they make sense, like from a logical perspective, because right now this just kind of looks like a bunch of nonsense, although you're probably like, okay, I can code this even if I don't know what it does. But let's see what it does. So we start here, I at 0, j at 1. You'll notice that we kind of ignore this f of 0 thing. Since it's an int array, failure table at 0 is set to 0 automatically. So we don't need to worry about that. You actually can get rid of this line too, because not filling in a value sets it to 0. So we look at pattern at 1 and 0. They don't match. I is 0, so it says fill in a 0 here and increment j. We look at indices 0 and 2. They match. So we're going to put a 1 here because I is 0 and we put in I plus 1 here. And then we move I and j forward. So I is here now and j is here. Now this A does not match with the B, but I is not 0. So we say I equals f of I minus 1. I minus 1 is 0. F of 0 is 0. So this is going to reset I back to 0, but notice that j doesn't move. This isn't anything getting cut off. There's no movement of j down here. This is the blast line. So j stays in the same place, and we check again, and you'll see that this time we do have a match. So you know the drill, we're going to put a 1 here, increment to j, and increment I. Now we have another match, so we're going to put a 2 here, because I plus 1 is 2. Increment I, increment j. We have another match, so we're going to put a 3 here, increment j, increment I. Now here we have a mismatch. So what's going to happen? I is not 0, so we do I equals f of I minus 1. So that's going to say I is 3, I minus 1 is 2, f of I minus 1 is 1, so this is going to say I should become 1. So I doesn't move all the way back to the beginning, it only moves back to index 1. We compare these again, we get a match. Since I is 1, that means we put a 2 here. Increment I, increment j. We get another match, so we get a 3 here. Increment j, increment I. We get a mismatch, so we do I equals f of I minus 1. So that's going to set I back down to 1. We get another mismatch. I is going to be set equal to f of I minus 1, which is a 0. We get another mismatch, and I is 0, so we just put a 0 here and increment j. And now j is past the length of our pattern, so we terminate. Alright, cool. What did we just do? Well, let's look at it. We have this, let's say at index 2 of our table. This is when we have only the characters A, B, A. Because remember, each index of the table only looks at the string up until that point. And you see we have a length 1 prefix and suffix match between the start of the string and the end of the string. That's length 1, so we fill in a 1 there. Similarly with index 3, we had A, B, A, and we have these A's that match up of length 1. And that's a prefix-suffix string. Now with the next character, A, B, we have now a length 2 prefix-suffix match between AB and AB. And it's very important that we always take the longest prefix-suffix match that's possible. Sometimes there's multiple lengths that we could pick. We always pick the longest, but we can't pick the entire string. We can't say, oh, this is length 3 because ABA matches ABA. No, we can only pick 1 or 2. So here we have a length 2 match. Likewise, for this string, we had a length 3 match between the ABAs. Then what happened when we added this next character? Why did our algorithm act the way it did? Well, what it did is it said, okay, before I had a length 3 prefix-suffix match. So the thing it checked for next is, do I have a length 4 prefix-suffix match? So does this ABAA match this ABAB? And the answer is no. But what it said is my length 3 prefix-suffix match, this ABA, within itself has a length 1 prefix-suffix match. So it says, okay, well I know this ABA matched, I know this ABA with ABA match is already here. Which inherently means this A and A also line up. Our algorithm already knows this because it's matched them before. So it says, okay, well I know I have a length 1 prefix-suffix match, maybe I have a length 2. And it determines that, yes, I do have a length 2 prefix-suffix match. And that's where we get this 2 here. And that's why that I skipped backwards by 1, because it was checking, do we have that length 2 prefix-suffix match, which we do. And a similar thing happened at the end. After we mismatched on the C, we checked, okay, do I have a length 2 prefix-suffix match? Okay, do I at least have a length 1 prefix-suffix match? Okay, I've got nothing. And that's kind of what the algorithm did. I'll give you a little bit longer to write that down or ask questions. Then we're going to talk about the actual algorithm itself and how it uses this failure table. Then we'll do an example. All right. You can pause if you need some more time, but otherwise, let's move on to the actual Kmp algorithm itself. So, unlike Boyer-Moore, but like brute force, we're just going to start comparing from the front of the pattern. Boyer-Moore is the only weird one where we start from the end of the pattern. We're just going to start from the beginning, I equals 0, j equals 0. Note that with the failure table, we started with j equals 1, but with the actual algorithm itself, we start with j equals 0. And again, I'll mention that this pseudocode uses slightly different pointers from what the, I believe, Sai Krishna slides use. They are the same algorithm, they're just using the pointers in different ways. Some people find certain methods to be more understandable than the other, but you can do whichever you feel more comfortable with. Some just make the edge cases a little bit easier to handle than others, but it is completely up to you. So, Kmp. If we get a character match, what we do is we just increment j. We move on to the next character in our text and pattern. And this is going to be like the build-up that we can use when we get mismatches. If we get a full match, we can add it to our list, which add I to the list, because that's the start of the match. Now, the reason I kind of put this here is what's going to happen is inside this mismatch case, I say, okay, if we have a mismatch, or if j equals m. Now, j equals m is only going to happen if we got a full match, because that means we matched character 0, 1, 2, all the way up through m-1, and after matching m-1, we incremented j to m, and that's how we get in this situation. Now, you probably want to reorder these to actually make that work in your code, but this made the more sense logically for talking about it. So when we get this mismatch, now we have these two cases. If j equals 0, this indicates that we mismatched on the first character of the pattern. And remember, with Kmp, mismatching on the first character of the pattern means we've gained no information. So all we do is we increment I by 1, shift it forward, look on the next character. Otherwise, what we want to do is we want index at failure table of j-1 in the pattern to align with the current text position. So the current spot we're looking at in the text, which remember the current spot we're looking at in the text is at index I plus j. So we don't want this to change, we just want our pattern to shift so that a different character is lined up there. How we do that is this little math right here. We do I plus equals j minus failure table at j minus 1. And then we reset j to failure table of j minus 1. Now you'll notice that I plus j hasn't changed here, because if we look at what it is now, it's I plus j minus fail of j minus 1. Remember, that's the new value of I, and the new value of j is failure table of j minus 1. So these obviously cancel out, and we're left with I plus j. So that hasn't changed at all, which is a really important property of Kmp, and some other index alignments actually express it a little bit better. But with I and j, this is how the math work out. And you'll notice that since we're looking at failure of j minus 1, with a normal mismatch, we never use the last index of our failure table. So the only time we use the last index of our failure table is this case right here, where j is exactly equal to m. Then we use a failure table at m minus 1, which is the last index. Which means that we're basically treating that after we get a complete match, we're treating it like we got a mismatch on index m. You'll notice that's not an index in the pattern. So it's kind of like we tried to compare nothing to some index of our text, and that's a mismatch. So that's kind of how the logic works, and it lets you condense a lot of your logic in Kmp by taking this full match case and shoving it in this mismatch case. Those work together very nicely. The next page is going to be an example. Don't forget that those are on the announcement if you want to write that out in advance, but I'll give a little bit more to write this down. It's overall pretty simple. The failure table is a lot of the complexity of this algorithm from like a theoretical standpoint, or like from a topic standpoint of how complicated it is. So the actual algorithm itself is pretty simple, but a little bit longer to write that down, then we'll do an example. All right, let's go ahead and move on. In landscape mode, we've got our text here, we've got our pattern here. If you don't have it written down by now, I recommend just pausing and doing that, or you can try to scramble and write it mid-example. But you'll notice I haven't filled out the failure table this time, and that's because I want to kind of show you a different method that's useful for filling it out that doesn't involve like writing down the I and j pointers, so it can be useful in a diagramming question. So when we fill this pattern, we fill this failure table out. Remember, index 0 always gets a 0. Then what we do is we look at our next index. If we're still at a 0, we just check, does it match the first character? So B is not the first character, so we keep it at 0. What changes is when we get a match of the first character. So to go from a 0 to a 1, that means we just encounter a character that exactly matches the first character. Now we encounter C. C is a character not in any part of the pattern before now. Automatically this is a 0, because it can't match with anything. Then we get a match with the first character. Remember, that's a 1. The second character, since we just had a match with a 1, we want to look if it matches with the next character. Do we have a length 2 prefix suffix, which we do. Now after that, we look for a length 3 prefix suffix, which we have. Remember, the values of the failure table can only at most increase by 1. So from a 0, we can only go to a 1. From a 1, we can only go to a 2. We can go down potentially by however much we want. So either all the way down to a 0 or down to something smaller than that. But we can only ever go up by at most 1. And that's a cool property. So we've got this failure table. Now let's start doing our algorithm. We match with this A, we match with the A, we match with the A. Now here we mismatch. Now we mismatched at J is equal to 3. So we look at f of j minus 1, which is f of 2, and we see that's a 1. So what this says is take index 1 of our pattern, which is this b, and line it up with this exact same column. And you'll notice what we've done is we've said, okay, I matched this a, and I knew that this a matched up with the exact same first character in our text. So I just took this a and lined it up here. So I know for a fact this a has to match. There's no point in comparing it. So I do not do any comparisons on this a. I start comparing here. And this is a really big important thing about Kmp. Once we match a character in the text, we never compare it again. So here we do a mismatch, so we compare it again. But here, what this means from this diagram perspective is every column should contain at most one circle without a line through it. So at most one successful comparison. No column should have more than one of those. So let's keep going. We match this A, we match this C, we match this A. Now here we get a mismatch. And this happened with J is equal to 5. So we look at F of 4, which is a 1. So it says, okay, line up index 1 right there. And you'll see we did a pretty big shift there. And remember, we don't recompare any of these characters. We start from that exact same character we mismatched on. Although here, unfortunately, that's still a mismatch too. And that happened with j equal to 1. So we do f of 0 is 0. And we line up index 0 of our pattern there. We try again. This is a mismatch, and since we mismatch at the very beginning of our pattern, remember we don't have any information built up yet, so we just need to shift by 1. So you can kind of see what happened here is we built up all this information across these matches, and we used that information to make a large shift when we got a mismatch. So let's start comparing. A, B, A. We get a mismatch. That's the same j equals 3 case we did before. So we know that we're going to try to line up this A here. And we don't compare here. Remember, we start comparing here again. This is another mismatch. And that was that j equals 1 case. So we understand that we're going to line up like this. A, B, A, C, A, B, A. Complete match. Now, remember that with Boyer-Moore, complete matches didn't really tell us anything. Obviously, it tells us where the pattern's in the text, but we don't get to do intelligent shifts after complete matches in Boyer-Moore. Not the case with Kmp, because remember, Kmp gets information from these matches. So a complete match should let us do a pretty smart shift. So what we do is we treat it like a mismatch on this character. Note, not the last one we matched with, the character afterwards. We treat it like we mismatched on that character. So, then what we do is we say, we look at j equals 7, which is that pattern.length. F of 6, j minus 1, is 3. So it says line up index 3 of the pattern right here, which is that C. And you'll notice what that did is it took that ABA at the end of the pattern and matched it to the ABA at the beginning. And notice we don't have to compare any 3 of these characters again. We start here, C, A, B, A, and we find a second match with only 4 extra comparisons. Now we would try to do another shift again, matching up like this C over here to line up this ABA over here. That obviously goes past the end of our text, so we're done at this point. We can count how many comparisons we did. You guys can just count the circles for yourself. But you'll see that we made these relatively large jumps at some point. We did a lot better than something like brute force would have done, where brute force would have just shifted this over by 1 a bunch of times to get past this D, versus we were able to, in 3 shifts, get past this D. Now, Boyer-Moore could have done that in 1, but Boyer-Moore wouldn't have done very intelligent shifts over here when we got these complete matches. So that's kind of the big difference in how these algorithms work. Give people a couple more seconds to write that down, then we'll talk about efficiencies and move on to Rabin-Karp. People can pause if they need a little more time. I'm just going to try to make sure I get through everything today, so I don't want to waste too much time right now. Let's talk about Kmp efficiencies. Now, worst case for Kmp is super cool. It's only m plus n time. Now, where that comes from is this O of m comes from creating the failure table. That part should be clear. And this O of n is going to come from iterating through the text. A cool thing about Kmp is each character is only compared a constant number of times compared to the pattern length. You'll see, if you remember from the example, that the only time where we compared a character a bunch of times in the text was right after we get a lot of matches right before it. So we can only do a number of character comparisons on a single character proportional to how many comparisons we did on all the or how many matches we got on all the characters before it. So we can only get these like times where we keep trying over and over again. Those only happen after we get a bunch of successes where we obviously didn't do a bunch of those comparisons. So we get this really nice O of m plus n, and I encourage you to mess around with it, try to come up with some bad Kmp examples, and see that it still works out pretty well and you don't ever revert to a real brute force. Best case, first occurrence, trivially, that's O of m. All occurrences, that's going to be our classic m plus n. We create our failure table, we iterate through the text, mismatching on the first character every time, so we just keep shifting by one till we get to the end and that's done. Now here we can actually define an average case, but like this kind of just falls in obviously because our best case is O of m plus n and our worst case is O of m plus n. So our average case is kind of obviously going to be m plus n. And that's just because these comparisons are done a roughly constant amount of times. So we just kind of iterate through our text. Sometimes we stay there for a little bit, but in general we're going through our text pretty linearly. Now in comparison to Boyer-Moore, Kmp is going to work better for smaller alphabets, because with these small alphabets, we're more likely to have these prefix-suffix matches. So you'll notice that a lot of the Kmp examples we do have a lot of like A's and B's and C's. We don't include like the whole alphabet because those aren't going to have a lot of these long prefix-suffix matches, which let Kmp do these larger shifts. Now, what's a situation you see this a lot? DNA sequencing is pretty common because you've only got 4 characters to work with. Or an RNA, you've still got a different 4 characters to work with. So with only 4 characters, you're going to have a lot of matches. Or maybe if you're looking for your favorite sequence of numbers in pi, numbers only have 10 possible things for each individual character. So you might have, with a long enough sequence, you might have prefixes and suffixes that match up. So it can work well when you're constrained to a smaller alphabet. But with large alphabets, that's where Boyer-Moore shines, because that has a much better best case than Kmp, even though Kmp has this really nice average and worst case that never devolves into brute force. Another really cool thing about Kmp is it never needs to go backwards in the text. Every time we're either comparing a character in the text, we're either continuously comparing that character multiple times, or we're moving forward on to the next character. Boyer-Moore occasionally needed to go back and compare characters that we've already looked at before. So if we're getting our text as a stream of characters one by one, instead of like stored in memory, maybe this is some super long string that we're looking through, or maybe this is someone typing input and you're searching in real time, and you're getting these characters one by one, that's what Kmp can do really well, because it never needs to go backwards. It can forget about everything it's seen before, because that failure table and the matches it's gotten so far, and give it all the information it needs. A couple more seconds on this, and then we'll move on to Rabin-Karp, which is probably the weirdest of the ones we're talking about. All right, feel free to pause if you need a little bit more time, but then we'll go ahead and go on to our final algorithm of the day, and our final pattern matching algorithm, Rabin-Karp. Now, Boyer-Moore and Kmp have a lot of parallels between them. Rabin-Karp is just kind of its own thing, and yes, that is the correct pronunciation. It is Rabin-Karp. We used to get it wrong, like a couple other things in this course with pronunciations, but this is the correct way to say it. Now, Rabin-Karp is going to use hashes. And what it's going to do is it's going to use these hashes to avoid doing comparisons when it knows that a full match has to be impossible. Remember that if 2 things are the same, even like 2 strings, and we hash them, if they're the same, they have to hash to the same string, or to the same number, which means that if they hash to different numbers, it's impossible for them to be the same string. That's kind of the basic idea that Rabin-Karp runs off of. Now, what we do is we pre-process the pattern to get the hash of the pattern. And the hash of the pattern obviously never changes because the pattern stays the same the whole time. Then what we do is we use what's called a rolling hash. No, dropping my pen and having it roll across the page was not intentional, but does have comedic value. But we use a rolling hash for the characters in the text that we're comparing. And the basic idea is this roll should only take O of one time. We should be able to do it very quickly. Just like hash codes were with hash maps were supposed to be super fast to compute, these rolls of the hash should also be fast to compute. Now, the hash function we generally use in this class is this monster right here. The first character of our pattern times some base raised to the m-1, plus the next character times base raised to the m-2, all the way down to the last character of our pattern times base to the 0, where base is like a large prime. I think it's like 109 or something on your homework, or 113, something like that. We'll use large numbers, and that's going to cause... what this model does is it causes two strings that even have the same characters, but in a different order, it causes them to have different hash values. And it turns out that this hash lets us roll it efficiently. Now, how do you calculate this hash efficiently? You might say, oh, cool, wasn't able to use a power method during homework 8, but now I have this powers I can calculate, but we're still not going to use powers. What we can do is if we start from the back, this, remember, base to the 0, that's 1. Any number raised to the 0 power is 1. Then the next character requires base raised to the 1. Then we need base to the 2, base to the 3, base to the 4, so on and so forth. So we can keep a variable that's equal to 1 at the start, multiply it by the last character of our pattern, add it to our continuing hash, then move on to multiply that kind of multiplier. It's not a divisor anymore, it's a multiplier. Multiply that by base, so we increase the power of it, then move on to the previous character. And if we do that strategy and we calculate the text hash and pattern hash at the same time, we can do this really efficiently in O of m time. We don't need to worry about like recalculating all these base to the m-1s or whatever. We can calculate this really efficiently if we start from the back, which is kind of cool. Now, how do we roll the hash? So this is going to be the example I use, this ABCD. We're going to say our current hash comprises the characters ABC, and we want to roll it forward so it comprises the characters ABCD. So this is the hash we're starting with. A times base squared, B times base, C times this, remember this is 1. We first take away the old character, so we subtract this A times base squared. We are left with this. Then we're going to multiply everything by base to increase its power. I knew I was missing something. We multiply this entire thing by base to increase the power of all of these bases. So you'll see that's going to leave us with b times base squared plus c times base to the first. And then we add our new character on. So our new character is d. And you'll notice here I've written it as d times base to the 0. But obviously base to the 0 is 1. So this is the same as if I just added on d. So that roll is super efficient to compute. Now you might think, oh, but this exponent seems like it's slow to calculate. But the nice thing is this is just base to the m-1. Every time it is base to the m-1. That never changes no matter when we're rolling the hash. So we can just store this in a variable after we calculate our initial hash and use it over and over again without recalculating. So we don't need to recalculate. All right, a couple more seconds, then we'll move on. Also, a lot of this information about the hash is, I believe, in the homework PDF / the Java docs. So you can read more about it there. Next page, we'll talk a little bit about the algorithm, which is super straightforward. Do a quick example, and then that will be all the content. All right. As always, pause if you need a little more time. I know I'm kind of moving a little bit faster through this end stuff, but just want to make sure we get through everything with a little bit of time, so I'm not eating all your time on this beautiful night. Although maybe we should go through more time, but let's see. We'll save some time for our example, and then obviously we can do our weekly card trick at the end. Rabin-Karp algorithm. Notice it keeps getting shorter and shorter how much of the page I take up. So, step 1, calculate the pattern hash and the initial text hash. Remember, initial text hash just means the first M characters. That's that first alignment we're going to do. Then, if the pattern hash and the text hash are ever equal, we're just going to brute force compare character by character until we either get a mismatch or a complete match. We don't do any fancy shifting, it's just brute force compare character by character. Otherwise, if the hashes don't match, we can roll the hash to the next character. And remember, just a reminder of the math, it's the same thing I wrote on the previous page, just in one step. We take our old hash minus the old character, that's that first character in the window that we're taking out, multiplied by base to the m-1, which we can save in advance, we don't need to recalculate. Take that whole thing, multiply it by base, just to increase the powers by 1, and then we add our new character onto the end. And remember, this is the same thing as if I said new character times base to the 0, because base to the 0 is 1. So this is our roll. It is constant time. This does not need to be recalculated. This is something we can very easily index to our pattern to find. Same with this. This multiplication is very straightforward, and obviously we've stored this value. So all of this is a constant operation. There's nothing fancy we need to do. And if we're finding all of the occurrences just after we get our complete match, we just roll the hash forward normally, just like we would if we got a mismatched hash somewhere. It's basically just a smart brute force, where we do our brute force comparisons, except we avoid doing comparisons when these hashes don't match up. And that's going to let us avoid doing a lot of comparisons that brute force otherwise would have done. Next page is going to be the example, so if you want to make sure you write that down in advance, you can go pull up the announcement. But otherwise, a couple more seconds and we'll move on to that. All right, example time. Now, something I want to note for this example, just for convenience of not having to do huge calculations, we're just going to say A is 0, B is 1, C is 2, D is 3. That's going to make this math really easy. And we're just going to use base equal to 1, which means that the hash of each of these text windows is just going to be the sum of the characters in it. So our pattern is ACC, and its hash is just going to be 0 plus 2 plus 2. Obviously, this is a little different from how your homework works, but we just want it to be something that's very easy to kind of see the basic idea of how Rabin-Karp works. So, we start here. We look at our text hash. That's these first three characters, A, B, D. That's 0 plus 1 plus 3 is 4. That does match with our pattern hash, so we're going to try comparing. So A matches up. Now this does not match up. So we stop comparing and shift by 1. Now we recalculate our text hash. It's going to be for this BDA. And we can see that's going to be this minus the A, which is a 0, plus the A, which is another 0. So this is also going to be the same 4. So we try comparing. This fails, so we shift. Now we've got DAA. So what happened, we took away a B, which is subtracts 1. We added on an A, which adds 0. So this is 3 now. And from a diagramming perspective, you could really easily recalculate this yourself. We see that this hash of 3 so remember, it's the sum of all these values, so it's not like concatenated values. So this is 4, not 22. So here, we have a mismatch of our hashes. So we just roll by 1. No comparisons. Now we've got A, B. So we took out a D and added in a B, so this has a hash of 1. That's a mismatch. A mismatch of the hashes. So we shift by 1. A, B, D. We know what this one's going to be. We took away an A, added a D, that's going to be 4. So we try comparing. We get our mismatch. Now we've got B, D, C. We took away an A, which is 0. We added a C, which is 3. That's going to be a hash of... C is 2. So that's going to be a hash of 6. That's 1 plus 3 plus 2. Obviously a mismatch, so we keep rolling. Got DCA. We took away a B. We added on an A, so that's going to be a 5. That's a mismatch, so we keep going. Now here we've got CAC. So we took away a D and added in a C. That's going to give us 4. So we do try to compare here. We get a mismatch immediately, so we shift. And then here we've got ACC. So we took away a C and added another C, so the hash didn't change. Now we have a match of hashes. Match the characters, and that finds a match. So you'll notice we did like a lot of these alignments, but we didn't do that many comparisons. If we look, we only did 1, 2, 3, 4, 5, 6, 7, 8, 9 comparisons through this whole text. That's pretty low compared to something like, especially brute force, would have done comparisons on all these rows, even a lot more comparisons on some places like these where characters matched up a little bit. So Rabin-Karp avoids doing all these unnecessary comparisons via this hash function. And with a better hash function, so if we used a base that wasn't 1, if we used like base of 91 or something, what would happen is we would, in a lot of these cases where the text hash appeared to match up with the pattern hash, those would go away, and we might have avoided doing any comparisons until we got down to here. So by using better bases, you can avoid these, but for the sake of this example, obviously we wanted to pick cases that have collisions. But if we use a base that isn't 1, those collisions aren't going to happen. So we have to use like a base of 1 or 2 to have any chance of collisions occurring. So I hope you understand why we use something like that. Even if it maybe isn't very realistic, it gets you the idea of how the algorithm works. A couple more seconds, we'll talk about efficiencies and have our end of recitation card trick. Right, as usual, feel free to pause if you need a little bit more time to write this down. Obviously, you can always plug like this example into the Viz tool. I think the Viz tool works like this, so you can get the same description, the same like result for any of these 3 examples we've done today. But our final page of the day, the Rabin-Karp efficiencies. Now, unlike the other algorithms, Rabin-Karp, we can kind of define an average case pretty well, because the hash is usually not going to match up unless it's an actual match. So in general, we're just going to be rolling and shifting by 1 without doing any comparisons, which means we have this O of m to calculate the initial hash, and this O of n to iterate through the text, where we're not going to have like any extra comparisons because we're almost always not going to have collisions. We're almost always just going to have that hash mismatch, and we just keep rolling forward. That's going to give us m plus n. Now, the worst case is if we did have a hash match on every single alignment. So for every single alignment, we needed to compare character by character, and then that just becomes brute force. If you think that, oh, like maybe this is impossible somehow, imagine just like a text of all A's and a pattern of all A's, where it's going to be a pattern match because it's an actual match at every single alignment. So something like that can work. In best case, you should be used to seeing this as now our single case, trivially, O of m, find a match immediately. For all occurrences, that's going to be that O of m plus n, where you just roll through the entire text with no or few comparisons. You should be used to seeing these cases by now, because they happen for most things, other than a Boyer Moore, which has its weird things. Remember, don't use math.pow. Use that running multiplier I explained. You can always ask about it on Piazza if you're not sure, but I think we have examples of kind of how it works in the PDF. Don't use math.pow. Don't write your own power function. Both of these are wrong. You will get efficiency deductions for these. But that concludes the content of today's recitation. I'll leave this up for a couple more seconds for people to write things down. Then we'll do a quick card trick, and I will unfortunately release you back into the real world. All right. I think that should hopefully be good enough. You can obviously pause on this. So let's get to our card trick. Let me pull up my screen so I can actually see what I'm doing. So this is actually a card trick I've been kind of thinking about doing for a while. But the biggest reason I didn't do the card trick up until this point was actually because this card trick does require a spectator to help me out with some things. But fortunately, I got my good pal right here with me to help me say hello to Ventus Alpha Percival, here to help me out with this card trick. He's even got some friends along to help be some spectators, watch what's going on, make sure I don't do any cool, weird magic trickery. He's going to be my spectator for this trick. So, how this trick works is I've got these two cards here, Ace of Clubs and Ace of Spades. So I'm going to ask Ventus Alpha Percival to, which I'm just going to call Percival from now on to save some time. I'm going to ask him to pick one. I'm going to look between them, and he's going to end up choosing the Ace of Spades. So, what will happen is I'm going to give him the Ace of Spades. So, fortunately, he can hold on to it just fine. And then the Ace of Clubs is then going to be my card, so I will give him that too. So he's going to need to keep track between the Ace of Clubs and the Ace of Spades and the Ace of Clubs. He's going to need to keep track of which one is his card and which one is my card. So I'm going to take them from him. I'm going to switch them around a bit. And I'm going to give them back to him. Got to make sure he can actually hold on to him. And then I'm going to ask Percival, okay, which one of these is your card? And he's going to think about it for a couple seconds and say, okay, it's this top one. This top one's my card. So I'll take that card he chose from him. And now, I've just put it on the bottom of the deck. I'm going to say, okay, would you guys be impressed if this card was actually the Ace of Clubs, my card, after following all that? You guys probably would be pretty impressed, because that would be like some crazy magic. No, it's the Ace of Spades. He got his card correct. But now I'm going to do some real magic. So I'll give him his card back. Except this time, I will do just some real magic. And now, I'm going to ask you guys if you guys would be impressed if somehow the cards have switched. So now this top one is the Ace of Clubs and this bottom one is the Ace of Spades. And I imagine most of you probably would be kind of impressed if I had done that. But unfortunately, something I haven't told you up to this point, the purpose of this trick wasn't actually to impress you guys. The purpose of this trick was to amaze you guys. Let me take these two cards from Percival and show them to everyone. And that is the true magic of Halloween, or something like that. I don't know if there was much of a moral to this card trick, but it's about 6:15, so I need to unfortunately release you to the real world now to deal with life's problems and all that entails. Hopefully you've enjoyed these card tricks. I should hopefully be able to find the tutorial of that to post in the announcement next week. I'm just going to wait for it to catch back up to real time and then end things off. Thank you guys for coming.